Well, we've made it to the end of Chapter 8, hypothesis testing, this time about standard deviation. So claims about the mean can use either the z or the t. Claims about proportion always use the z distribution. And then you may remember, whenever we're using standard deviation, then the test statistic and critical values are going to be chi-squared. So chi-squared formula is very short and sweet. Here you go. It's basically degrees of freedom, the sample standard deviation, and then this would be the number coming from the claim, sigma. And this is not in the calculator. You need to type that in yourself, but luckily it's pretty small, easy. Another thing to remember is chi-squared is not symmetric. So you'll have to look up the right tail and the left tail separately. And also, there are no negatives. They're all positive values. And we're going to use table A4. As you may remember, I split mine in half where this is going to be the right tails and these are going to be the left tail critical values. All right, so let's get started. So for college exams where they're worth 100 points, the standard deviation should be 15. And there should be a fairly normal distribution for those means. Anyway, the main point is the standard deviation is supposed to be 15. How does that compare with first graders? Do you think there would be more variation or less variation for first graders? I think there would be more variation. Let's see. So we're going to test the claim that it's not 15. So maybe it's over, maybe it's under, but it's not equal to what it is for college students. So here's the information that I got. The students were tested on 100 spelling words. Here's how many they got right. Now, up until now, I've been just giving, here's the mean, here's the standard deviation, and equals. But from about this point on in the semester, we're going to need to start dealing with raw data, so we might as well practice some right now. So with this list of data, which is how many words they got out of 100, you need to put that in a list, and then find the mean and standard deviation, although for this section the mean is not relevant. All you need is the sample size of 21 and the standard deviation S. So here's the sample data that we need. Alright, now let's go do the hypothesis test. So the claim is that it's not equal to 15, so it's not the same as college students, and H1 is the same, making it a two-tailed test. And of course H sub O always has equals, and this right here should say 15. I'll fix that. So here's the sample data, and we're using alpha equals 0.05. So it's a two-tailed test. It would look like this. Degrees of freedom is n minus 1. Take the 0.05, cut it in half, so 2.5% on this side, 2.5% on this side. And now take a look at table A4. So we need degrees of freedom of 20, which is right here. And then if we're using on the right side 0.025, that would be this column. So that's a 34.17. And then connected to that is the 975. And if you go down here, it's a 9.591. So there are the critical values. So basically, if the test statistic lands between 0 and 9.591, we're going to reject H sub O. And if it lands in here, past 34, we're going to reject H sub O. So now it's time for the formula. Like I said, you just need to type this into the calculator yourself. This is degrees of freedom. This is the sample standard deviation squared. And then the number from the claim, 15. That turns out to be a 101, which obviously goes past 34.17. So reject H sub O, which means we actually did prove something. And actually, since this lands to the right, that means the standard deviation is much higher. As you can see from the sample, this is much higher than a 15. So the claim is true. The standard deviation is not the same for first graders. It's actually much higher. There's a lot more variation for the scores of first graders. Mostly that's because when you compare college students, the college students are ones that have succeeded not only first grade, second grade, all the way up to 8th grade. They've also succeeded high school and they've enrolled and are in college. So they're much more of a homogeneous group. They've obviously succeeded in school so far, so their scores are going to be much closer. All right, here's a second example. So there's this automatic, and you know what, you can do this with any machine. You can just say this automatic machine is supposed to do such and such, and the standard deviation needs to stay below. So in other words, when it's an automatic machine, there's going to be some variation. It can't be 100% accurate every time. So in here, the technicians could say, well, we believe that the standard deviations should be below 0.5 ounces. And if it goes beyond that, then there's too much variation. There's something wrong with the machine. We need to fix it. So then this machine, one particular machine, was tested 43 times. The mean was pretty good, pretty close to 12 ounces, but the standard deviation is a little bit too big. But is this big enough that you should say, you know what? This thing is starting to get out of control. We need to pay to send a technician out there to fix it. So has it gone far enough beyond the 0.5 ounces or not? So this process that I just described is also called statistical process control, where in manufacturing situations, they'll watch the statistics over and over again every hour, every minute, every day. And when they start to see the numbers get out of control, so they're not even looking out on the manufacturing floor or whatever it is, but they're looking out at the numbers. And when the numbers start to have too much variation, they say, hey, wait a second, there's something wrong, we need to check it. That's this type of situation. All right, so the claim is that there is too much variation, so that it's gone beyond what they said it should be. That's going to make it a right-tailed test. Here's the sample data. We don't need the mean because the claim is not about the mean. The claim is about standard deviation, so we just need this information as our sample information. So it's going to be a right-tailed test with 0.05, and then we need to look up degrees of freedom 42. Well, here, you notice that there is no 42, so what you do is you use what's closest to 42. That's going to be a 40. And we need to go over to the right tail, 0.05. So that's going to be right here, 55.758. Notice what I also like to do is cross out the 42 and say I used 40 because that was the closest they had. So 55.758 is the critical value. Now we just do the formula for chi-squared. So this is the sample standard deviation squared. This is the number in the claim squared. Degrees of freedom goes right here. And then it turns out to be 87, which definitely goes past 55. So once again, we did prove something. So reject that it equals 0.5, which means that it's actually past. So the 0.72 is proving, yes, it's definitely past 0.05. So the claim is true. It's gone past what it's supposed to. So the machine does need to be repaired. Call someone out. All right, we're now done with Chapter 8. Hey, in Chapter 9, the good news is it's hypothesis testing again, except instead of just one mean, it'll be two means. Instead of one proportion, it's two proportions. But all the main principles and all the main steps are the same. So Chapter 9 is not going to be too much new. I'll see you there.